Stop treating your data like a flat pile of documents. We have a fundamental problem with modern RAG systems. We dump millions of vectors into a database and hope that mathematical similarity equals actual understanding. It doesn't. Vectors are fuzzy. They guess. To build agents that can actually do work, we need precision. We need to move from flat retrieval to structured reasoning. Today, we are not just building a search engine, we are building a knowledge graph. Here is the trap that most developers fall into. Vector databases are incredible at finding things that sound alike. If you ask for Apple revenue, it retrieves documents containing those words, but they fail at relationships. If I ask, how did the CEO's strategy change cause the drop in engineering budget, a vector store fails. It just looks for keywords. It doesn't understand causality, time, or hierarchy. It returns a bag of concepts, not a map of truth. This disconnect is the primary source of hallucinations in complex agentic workflows. To fix this, we architect a system that mirrors how the human brain actually stores information, via connections. We define nodes, which are the entities like a person or a file, and the edges, which are the relationships like wrote or depends on. When a user asks a question, we don't just scan for the text matches. We use an LLM as a translation layer to generate Cypher queries. This allows the system to traverse the graph, hopping from node A to node B, following the specific edges to find an answer that is structurally guaranteed to be correct. We are keeping our build stack precise and production ready. We are using Neo4j as our graph database because it handles dense connections better than any multimodal database. We are using LangChain specifically for this GraphCypherQAChain, which abstracts away the complexity of prompt engineering the LLM to write valid database queries. And we're gluing it all together with Python. This is the standard stack for RAG 2.0. Enough theory. Let's open the terminal and implement this. Before we start coding, you need to make sure that you have Neo4j installed on your machine. Here I'm using the desktop version for Windows. I'll leave a link in the description so you can download it as well. First we need to create a new instance. Let's call this test database. We need to specify password. It needs to be 8 characters or longer, so I'll just type password to be our password. That's for simplicity. In production, don't do that. And let's create our database instance. When it has been successfully created, you will see the status as running. Once the database is set, we need to add one more plugin, which is APOC. This plugin is useful for things like collection manipulation, graph algorithms, and data conversion. Let's install it. To do that, you need to restart your instance. Now it's time to start coding. Let's open our terminal and create a folder called GraphRAG and also move inside of it. Then we create a clean virtual environment and we also activate it. Once we have our virtual environment active, we need to install a few dependencies. We need LangChain for the orchestration, Neo4j to talk to the database, LangChain OpenAI for the reasoning brain, and the LangChain community for the graph wrappers. We also need .env to load our environment variables from the .env file. Let's install those. Now we need to create a new file called .env. Here we will put our environment variables. For this video we will need OpenAI API key, where you should put your real OpenAI key, and we also need some Neo4j environment variables. We will use those to connect to our database. Next, we need to create our Python file. Let's call it graphbuilder.py. We start with our imports. We aren't using the raw Neo4j driver here. Instead, we are pulling in Neo4j graph from LangChain. This is a high-level wrapper that manages schema retrieval automatically, a critical feature we will discuss in a moment. We also import chart OpenAI because generating database queries requires a model with strong logic and code generation capabilities. We also bring in the GraphCypherQAChain. This is the specific chain designed to turn English into Cypher, the query language of graphs. And we also import load.env in order to load our environment variables. Now we instantiate the connection. This Neo4j graph object does more than just open a socket. Pay close attention to the graph.refresh schema. An LLM is blind to your database structure unless you tell it what exists. This method scans your database, identifies every node label and every relationship type, and formats it into a prompt context. Without this schema injection, the LLM is just guessing at table names. We also print the schema to the console so we can verify exactly what the agent sees. A graph is only as good as its connections. A vector database would just store these sentences as flat text. We're going to do something different. We're going to strictly define the relationships. We are using a raw Cypher query to see the database. We create projects, a manager, and a dependency. Look at the merge statements. We explicitly define that the manager manages the project and the project depends on the GPU cluster. These edges are the pathways our agent will walk to find answers. We're hard coding the logic into the data structure itself. Now this function is the engine room. We initialize chat OpenAI with GPT-4o, and crucially we set temperature to 0. We are asking the model to write precise database code, not poetry. Any creativity here leads to syntax errors. We then wrap this in the GraphCypherQAChain. When we execute this, it performs a 4-step dance. It reads the user question, looks at the graph schema, writes a Cypher query to retrieve only the relevant data, and then uses that data to answer the user naturally. We enable verbose equal true because as builders, we need to see the generated Cypher query to debug the logic. Now let's wire it all together. We connect to Neo4j, we see the data, and then we ask the killer question. We ask which manager has projects depending on the GPU cluster. Think about that. The name Alice is nowhere near the words GPU cluster in our data. They are separated by a project node. A vector search would likely fail this or hallucinate. But our graph engine will traverse the manager's edges to the project and then the depends on edge to the dependency, flawlessly linking the manager to the resource. Let's now run it and watch the logic unfold. Open your terminal and run python graphbuilder.py. When it's done executing, you'll see that it performed what we wanted. It understood our data and provided us with the correct answer. You can see the full context here and also the generated Cypher query. We have successfully shifted the paradigm. You're no longer relying on probability and keyword matching. You're relying on defined structure and relationships. By combining the reasoning capabilities of LLMs with the structured storage of a graph database, you eliminate the blindness of standard vector retrieval. The code for this entire system is linked below. Clone it, swap out the seed data for your own documents, and start building systems that actually understand your data. If you enjoyed this video, please leave a like and subscribe. I'll see you in the next one.